All right, everyone, we're going to get started. So this is the high temperature heat pumps for space heating panel. I'm joined today by Jarvie with Flow Environmental Systems, Chris Devins with Trane, and Javier Aleman with Energy Machines. My name is Schauger. I'm a project manager and energy engineer with LaBella Associates. I work out of our Buffalo Bills office. We have offices all across the East Coast. We're headquartered in Rochester, New York. So today we're going to talk about high temperature heat pumps. I know a lot of us are either architects and engineers, building owners, even some utilities that have run into instances where you have existing buildings with boiler systems. Maybe they're gas-fired or they have fuel oil, and the terminal units in the building require high temperature hot water. It's a pretty standard application and pretty efficient application, but as our state and other agencies are requiring facilities to electrify their buildings, we're presented with the challenge of how do we replace this fossil fuel equipment and still condition our buildings. So say you have a gas boiler plant and you need to electrify it. Well, you're presented with maybe one option would be putting in electric boilers. Issue there is you probably don't have enough electric capacity, just based on my own experience. Another issue, you could rip out everything in your building and put a whole new system. Or, as we're going to talk about today, high temperature heat pumps can also be an option where instead of a traditional heat pump technology that can only maybe go up to 140 degree hot water, these technologies can get to the same temperature ranges as your current gas boiler equipment. So we'll talk a little bit about our technologies, the different products that our companies offer, as well as some of the control strategies and components of those technologies that will allow the heat pumps to get up to these high temperatures. So without further ado, Jarvie will go off first and talk about his products.
There we go. Hi, everyone. Well, hello, everyone. This thing is turned up loud. Hey, I'm Jarvie. I'm with Flow Environmental Systems, and we're focused on decarbonizing the heating and cooling market space, particularly around space heating. So if you're in the right room for that, welcome. Let's see. There we go. So just real quick, who we are. You might not have heard of us yet, but you're going to. We are a US-based company. We're specifically here to decarbonize and provide environmentally responsible refrigerant. For those really hard, challenging issues like decarbonizing, detoxifying, eliminating the need for fossil fuels, period, just stop burning stuff, and serving those harder to electrify end use cases. What are those? Low ambience, cold geo loops, exhausting the field, having backup dual fuel options, all this other stuff, as well as making high temp heat and heat recovery like we talked about before. So just to always premise this is going to go for all of the other panelists here today, but all building emissions account for about 40% of greenhouse gas, right? And we have a ton of existing stock, and we're building new New York City every month globally. So what are we doing about that? Us in this room, we're all heat pump nerds. We all like geothermal. We try to figure it out. That's the voluntary path. But there's this whole regulatory side for everybody else to jump on it. And that's where we start coming into this levers for electrification of heat, because we're kind of at peak chiller and boilers. Now we got to electrify the heat, get rid of start talking about heat pumps a lot more, and what refrigerants are in those heat pumps. So with that, I just want to give you a really grounding for all of our conversations that we have as we go into this next generation of technologies that are coming out. There's really a wonderful grading rubric that our regulators throughout the country have come up with, and it's really global warming potential, ODP, ozone depletion potential, don't blow any more holes in the atmosphere, please. Safety class, we want non-toxic, non-flammable, and we want pollution-free, no PFAS, no adverse health effects, damaging drinking water, forever chemical things. And so we're really left with a very rudimentary chart of what's available as manufacturers of building stuff. What are we going to use? We're phasing out 410A, we're phasing out 134A, GWP, right? Don't add more holes in the ozone layer, please. Safety class, we want to be safe for building operators to use things, and then no PFAS. We're really limited in our choices then at that point. And this is where all the new refrigerant transition paths are coming from when you look at this. And we're in the room today to talk about high temperature heat pumps too. And so there's another chart here at the bottom. And now that actually tells you the fundamental limits. Most heat pumps are limited by a high pressure peak, and you can see that where they are. And there's a few, if we're talking high temp, we're talking above 140 degrees. And if we're getting NYSERDA's dream job, we're talking about 215. So what are we actually making? Well, we're limited further, and we got to create something. And so I'm going to argue today on my behalf for CO2, and that's exactly what we're building into products today. So all those other refrigerants you saw on the list besides CO2 are subcritical. They condense, and they have a condenser to them in their system. We make a transcritical CO2 heat pump. It's a little different, but it allows us to now take 100% sensible energy out of the air. It allows us to do interesting things like optimize for heating and make a really efficient high temperature heat pump or boiler replacement, as well as make it a good chiller and balance it anywhere in between for a great heat recovery or a geothermal or an unbalanced water to water situation. So even in those high temperature deliveries, we can start downsizing our geothermal loops even more to optimize the system. And on top of that, we can do some other magic like no defrost and air source and so on. So knowing all this, we actually built it into a product for everything that we do. We specifically focus on HVAC duty for what we are. We have air to water, which isn't GEO, but it's a nice backup option for your GEO well if you missed your calculations underground, or having a quick add-on to the system if something goes wrong. And then we have water to water, which is phenomenal for GEO. It's phenomenal for heat recovery and these industrial process elements of that where you got high temperature or low temperature heat recovery portions. Add in the fact that CO2 is one of the very first refrigerants ever. We borrowed all the old tech and made it new again and repurposed it for high temperature heating and cooling. Domestic water is a breeze. We can now truly and completely replace hot water boilers and do a unique simultaneous heating and cooling mode with no reversing valve. You just extract heat out at the modes you want. If you wanted to do something more, we have our just heat pump module. There's your water to water. You hook up power and water, you're done. Or we got the gas cooler side. You can hook to it as the backup or the primary, whichever way you need to go. You can split it by a huge distance, about 5 times more than the traditional DX, or we can package it together to make it all one shot. So just to show you a little bit more here, we have some different form factors and models of what we do. So we have through-door models, so you can do retrofits of high rises. You can roll them in the elevator through any standard service door, gang them up to do some amazing stuff. We have larger installations for our large buildings, our campuses, and so on. So we can do up to 120-ton modules to make that work. And if you get the gas core side, there's a variety pack you can choose from V-banks, horizontals, verticals, whatever configurations you want to do. Operational modes, they're easy to do and make. We can do cooling only, heating only, simultaneous, no reversing, you name the climate conditions, stuff like this is capable. If you switch to a refrigerant that has a range from -60 to 325 degrees in one fell swoop. So we make sure we align with all the industry best practices and make that work. So I'm going to kind of highlight this. We have our traditional systems, your furnaces, your chillers, your boilers, your geothermal loops, you name it. As we are in this transitionary step, we're kind of in our synthetic refrigerant phases of doing things. We have the ability to do all the work. It's just a lot of systems and a lot of complication. If we can simplify that down into more of like a centralized boiler plant that can share and optimize all that, now we can reduce things like defrost and air side. We can replace electric boilers. We can do low temperature cooling for those wells that have minimal glycol or antifreeze in them. Aquifer exchanges are now possible because you can do that without contaminating the groundwater source, because it's just above freezing. You do low delta T's. You can save a lot of space by combining a domestic water heater, a chiller, and a boiler together, and sometimes that's as much as 50% space reduction. In space-constrained spaces, that's a wonderful thing. And another really big one that comes out of all this, if you could do the simultaneous no reversing element, you don't always need a new power feed. Oftentimes you have enough power hooked up for a chiller or a cooling or your existing GEO side that you can minimize your well. You can minimize your power feed coming into the space and not have that big infrastructure adder and make something better. And you can actually now match your existing low profile of your buildings. So you use same temperature ranges, same temperature profiles. So you can phase out over time rather than gut it to the bones, redo the building, all new water pipes, upsize all the lines, and truly replace and work on what we're doing. So I'm gonna just highlight this really quickly since we're in New York. We're participating with the Empire Building, or Empire Technology Prize. NYSERDA's here, we're working with Wells Fargo, the Clean Fight is here, RMI, a lot of these, and Gilbar locally is our rep on this side. And we're really focused on making the greenhouse gas emissions of tall buildings and heating systems in particular, and taking a big swath and a big dent out of that. So if anybody hasn't seen that, take a look. There's some really great resources out there and knowledge and transfers and a lot of good opportunities. If you want to participate, there's lots of room for demonstrations and participation in this as well. So I'm going to leave you with some of the benefits. There's a lot, but what we're doing is making an engine that is now capable of interfacing with all kinds of things. It can make hot, it can make cold, but it also has a capability to integrate with whatever you want. Thermal storage, heat recovery, geothermal, optimize all that, and then just use the air side as a backup or a trim function if you need an additional unbalanced loads. And on top of a system like this, we find a really wonderful benefit of grid integration and interoperability. So we're working with the Lawrence Berkeley National Labs, Oak Ridge, DOE on a bunch of different things to make that all possible. And with this, we can do some really amazing stuff that give grid operators a chance to do something they haven't had a chance to do. And do it in a form factor where we can replace boilers, we can do cold, we can do it efficiently, robustly, good supply chains, and overall target the lowest cost of ownership possible. So with that, I am going to wrap it up. If you got any questions, feel free to ask them. Otherwise, you got a great panel in store for you today, and thank you.
Clicker, I apologize. Well, while they're figuring that out, my name's Chris Devins. I'm with Trane. I've been with Trane about 15 years. I lead our systems business across upstate New York. My decarb journey started in a bar about 8 years ago when an engineer started sketching out on a napkin how he was going to use the most efficient and reliable compressor he knew of to heat the city of Syracuse. In his professional opinion, that was a Trane centrifugal compressor. I happen to agree with that. But that was 8 years ago. I've come a long way in trying to understand and really dig deep into this world. We're all up here talking about how we can achieve temperatures we didn't think were imaginable 10 years ago. And so, we're up here saying, hey, we can hit 180, we can hit 200. But let's not then just settle there. I found a lot in these conversations that once we can prove to you that we can get to 180 and be at the table, now let's say why we shouldn't use 180. We really have to push back. I know we have existing infrastructure. Let's do some stress tests. We found a lot of systems that are sized for 180 can at a minimum handle 165 without any renovation, right? Let's not let the tail wag the dog. Let's not let the convectors drive the central plant. So let's really push back on that. We can hit these high temps, and we're going to dig into how we can do that. Trane has a kind of a two-prong approach right now to the decarb space. We are coming at it from a new technology standpoint, as well as from an innovation on the system side. So one of the things on the technology side is we've recently launched a national partnership with Aleman, an industrial heat pump manufacturer. There we go. Nice work. Thank you. What am I doing now? All right. Appreciate it. So we're going to focus on one line that we've got with Aleman right now. It's all reciprocating compressor base with VFDs. We've got a ton of different options for refrigerants in there, right? But what we want to focus on is, what we're doing in a lot of our equipment is figuring out how different refrigerants play with different compressors to suit that specific application. Here is shown the same exact piece of equipment with 3 different gases in it. R450, we can do 175 degrees of lift and about 200 degrees leaving water temperature, and that's more optimized towards the highest COP. If we switch that out to 513A, we're going to max out our capacity, suffer on the leaving water temp and the lift. Or if we go 515B, we're able to get over 200 degree leaving water temperature. Those are some of the things that we're doing, and it's not just with Aleman we're doing that with our traditional products as well, playing with different gases. Does anybody have a better name for the chiller heater out there? Because this is kind of what we're stuck on a little bit. It's a non-reversible heat pump. It's a ridiculous name, but I haven't found anything better. But all chillers can be heaters. We're just focused on what's coming out the back end, right? We can get you, with traditional equipment, put a different gas in it, we get up to 250 degrees out of a screw chiller. Like, that's insane. What do you mean it's a chiller? Well, it's a chiller heater, I guess. So if anybody's got a better name for that, would love to talk through that. But on that new technology standpoint, we're trying to figure out what we can do to our existing compressors and chillers to get that high temp. We're supposed to be able to do low pressure steam out of screw chillers in 2025. Doesn't quite compute in my head how we're going to do that, but that's insane. And that's with the same screw compressor that our techs nationwide know and love. Same controls, same exact piece of equipment, maybe a different gas in it. Right? So we can get on the smaller side, it's the same piece of equipment, different gas, let's get 200 degrees out of that. Right? But once again, just because we can get to 200 degrees doesn't mean we should. Same on the centrifugal side. We can do up to 180 degrees out of a centrifugal chiller. Same exact compressors, same exact controls. We know the tech workforce is massively strained, and finding that talented labor is a challenge. So let's not let's simplify their lives. Let's have them walk up to the same piece of equipment that they're used to and they've known for 20 years, and they can work on that with their eyes closed, right? There's a lot of benefit to that. When I talk about the system side, we're trying to innovate a little bit, and some of this is based on the challenges with lift. Compressors often don't really care about the temperature as much as that lift. Centrifugal compressors are typically max out around 75 degrees of lift. Screws, you can get 110. Recips, we just saw, you can get 180. That's pretty impressive. But how can we use standard equipment that we have available today to achieve that? So we're pushing a lot of cascaded systems, especially in northern climates on the air source side, where we're dealing with 0 degree ambient or maybe minus 20 degree ambient, right? We've got equipment that can do 180 degrees of lift at minus 20. That's awesome. It's also a really expensive, inefficient way to do that. Instead, what we want to talk about is splitting that lift between 2 pieces of equipment. So on the air source side, we'd be, rather than trying to do 180 degrees of lift or whatever out of that air-to-water heat pump, let's deliver 60 degree water out of that. That's going to increase that COP on that air-to-water heat pump, which is your most expensive, least efficient piece of equipment in the system, dramatically. We're going to be talking about COPs of 3 and 4 at 0. You can't typically get that with your traditional air-to-water heat pump. So then what you're doing with that 50 to 60 degree water, you're putting that into an evaporator of another chiller heater, and then doing another standard set of lift to get to your desired leaving water temperature. On the geothermal side, similar concept. Well-filled, let's say we're getting 45 degree water in to the evaporator on a low temp unit, which, oh, by the way, is every chiller you have in your buildings today. There's no difference in a low temp unit. We've got a lot of existing infrastructure. Let's not just throw it out, let's use it to our advantage. So we're gonna have that 45 degree water in, another standard set of lift, get 110 out maybe. Put that through a thermal Put that into the evaporator on the high temp side, which could be another centrifugal chiller or another screw chiller, and then do another standard set of lift. So when would you consider this? Obviously, high temp situations, right? That's a no-brainer, especially when we're talking larger systems. District systems, it's a huge opportunity. We're doing a lot of steam to hot water conversions. We're talking 30 million BTUs plus. They've got existing centrifugals, or they're very familiar with existing centrifugals. They like that technology. Let's lean on that. That's the most efficient, reliable compressor we have. Let's lean into that, right? Also, dual temp systems. Let's say maybe out of our central plant, let's have a decentralized cascade. Let's put 120 out of our central plant, and maybe those 3 labs on campus need 200 and there's nothing you can do. Let's put a booster in that basement, right? Put that 120 in the evaporator of a booster in that building alone, and then get your 200. Let's not drive the whole system to 200 when we don't need to, right? Or maybe that's at a building level. Hey, you've got air curtains that need 200 and we're not swapping those out. You put those in 3 years ago. Okay, we don't have to. Let's keep that as is. Let's boost it up for just that, but not have the whole system size for that so we can make jobs more feasible. So often on these electrification jobs, the dollar values just get way too high and the job just falls dead in the water, unless there's obviously significant regulation forcing you to do that. But the people that want to, that first cost barrier is a major barrier to have to overcome to make jobs happen. So we're able to utilize more standard compressors that our technicians know and love. It's coming off of standard manufacturing lines, and it costs a heck of a lot less than our than our specialized equipment that might be able to do 200 degrees of lift. Let's use that existing infrastructure, right? Let's not throw out those chillers. Let's use that to then tack onto and achieve our high temp. We often talk about simplicity or maybe the complexity of this system. Revolutionizing the way we're heating buildings is not going to be a simple job. Whether it's from a system level having added complexity, or whether it's in a black box in your mechanical room that might make it easier for the designer, easier for the commissioning agent, but then for the next 20 years, is that then simpler for the owner to maintain and operate? Or would they rather have the compressors that they've operated for 30 years? Something to be considered there. There is no simple fix for electrifying, especially existing infrastructure. This is an example of our centrifugal cascade, just some performance, and we can do 145 degrees of lift, which is pretty impressive. And we're still getting a COP of about 3. That's awesome. But once again, just because we can get there doesn't mean we should. Let's try to push that back on that and see what actually needs to be done. Maybe we can handle 80% of that campus at 140 degrees, reduce that lift. You see the impact on the COP. If we can drop that COP to 95, we're over 4. The lift to 95, we're over 4. That's pretty impressive for a 30 million BTU system, right? On the air source side, people sometimes accuse me of just trying to sell more equipment. That is my job. That is what I try to do. But if you look at the cost standpoint, it actually might make sense from a first cost. And this is a fairly small system, 6.3 million BTUs. If we're just going with specialized equipment that can do that 120 degrees of lift, hey, simple design, COP is going to be about 2, maybe $3 million first cost of the equipment only. If we switch that to a more standard set of equipment, only doing 50 degrees of lift on the air-to-water heat pump, and then relying more heavily on that water source, that water-cooled equipment, you're going to cut down significantly on that. What if we're talking back to 30 millions as an air source? Well, let's have a centrifugal chiller on the inside. Let's increase the resiliency of that system and increase the overall efficiency, relying more on the most efficient piece of equipment in the system. Here's a quick schematic on a steam to hot water conversion for an existing airport terminal. Quick layout there. It allows you to do heat recovery. We've got a 6-pipe heat recovery heat pump that can do simultaneous heating and cooling. It is that black box that sits in the mechanical room. Boom, easy, done. Does that make sense at scale? At larger jobs? Maybe. Or maybe we should be doing a low temp unit that is getting us 120 out of the condenser side and chilled water back to the cooling loop or to the well field, right? Let's shift those BTUs internally where we can. crank that outside air damper down to its minimum position, reintroduce those BTUs. You know, the days of airside economizer in upstate New York, like we want that cooling. We need to keep those in our buildings. So let's reintroduce those cooling loads, handle that with our low temp unit, and then boost it up from there to get up to our 200 degrees in this example. That's all I got. Thank you very much.
Good morning, everybody, or actually good afternoon. My name is Javier Aleman. I'm with Energy Machines. And what I wanted to do is start off with a brief introduction on 345 Hudson. It's, for those that are not familiar, it's a 1 million square foot commercial office building. Currently, it's in the middle of a multi-phased retrofit. At the end of the retrofit, the entire building will be hydronic heat pumps, both heating and cooling the entire building. And just to echo what was said previously, at the end of this, we're still forecasting on reducing kilowatt hour consumption. So the energy recovery and the thermal recovery and the whole process from the hydronic side and the air side will be so great, we're still going to shift everything to electric and reduce electric consumption. So this is a pretty powerful thing. So if you haven't seen the heat pumps, this is what they look like. They're both functional and aesthetic. It's a marketing piece, and part of this is also being able to tell the story, right? So people need to both get the functionality that you would expect out of the HVAC equipment, but if you can tell the story to your tenants and have that story, carry forward, it helps the cause here. So the LEDs actually change color. If it's predominantly providing cooling, it'll turn blue. If it's predominantly providing heating, it'll turn red. And so at a glance, you can kind of see what the plant is doing. So here's today's typical process in going through the construction process. There's your manufacturers in a silo, and there's a lot of great things that are happening there, but they're completely separate from the controls contractor, the engineers, and then the commissioning, right? So like all of this, if you've ever been through it, is a little bit like pulling teeth sometimes, especially in commissioning. If things are not working as expected, it can drag on considerably and just be painful for everybody. And so one of the key differentiators is that Energy Machines is a manufacturer, right? So we make the heat pumps ourselves, we make the energy recovery units ourselves. We're also a system automation BMS vendor, right? So we can turnkey that installation. We can do the equipment, the controls. We can help you with the energy modeling and the system design. So we're not stamping drawings, we're not being the engineer, but we will work with engineers and making sure that this design is going to work as expected at the end. And lastly, we'll commission it, right? So we'll help throughout that whole value process. So you get this vertical integration versus the silos that are typically seen in the construction process. And a lot of the innovation is not only on the controls and the equipment side of it, but partially also the business model of it. So we have a couple of heat pump families. We have our low temperature heat pumps that go up to 126, mid temperature heat pumps that go up to 150, and the high temperatures that go up to 180 and a little bit over. And these are all available in A1 refrigerants that are low GWP, R515B, or A2L refrigerants. So I think GWP of like 6 or something like that. So here's what you also get with controls that extend beyond just the chassis, right? So if you can extend the manufacturer controls into the mechanical room, you get a lot of like superpowers, if you will. So for example, there's no minimum flow in the machines or in the system design. Like the machine itself has limitations, but the system design has no minimum flow, no minimum turn down. You can get COPs on the low end, and this is for like the high 180 degree, while also hitting your chilled water set points in excess of 4. And on your lower temperature conditions, you can easily get into double digits, some of them even getting into the teens. You have a self-balancing system. It's easily expandable or contractible. So like basically you can design the system once, and add more modules if you need to add more capacity, or if the use ever changes, you can actually remove your modules and put them somewhere else that you need more capacity. And energy is redirected, right? So, where you're extracting heat, you don't need to have another source of heat. And so that's what you get there with controls. So with the thermal network, this is kind of how energy recovery is done on the chilled water side most days. And so the top, this thing's just going on its own here. The energy recovery on the top side is basically when the heating and the cooling loads magically balance, right? And this is like your unicorn scenario. If the chilled water side drops in capacity, by nature, your hot side has to drop, unless you can have some self-balancing mechanism that corrects for that. And so really, these next two scenarios are where you typically live 99.9% of the year. And so with this solution, now you have systems that are in excess cooling feeding systems that are in excess heating. And so you can extract heat from one floor, have your energy arbitrage in the condenser water riser, and you're essentially dropping in those BTUs somewhere else that you actually need. And so energy is shared between different systems, different floors, it's all connected, and you basically have a system that results in a much higher efficiency than you would otherwise trying to solve that in the box. Now here's a typical load profile for a building. Like this one happens to be a 1 million square foot building in Midtown Manhattan. And they all can change, but this happened to be this one. Now the way that most energy recovery is done, as I showed in one of the other slides, is trying to find that magical little sliver where you have heating and cooling that overlap. And then you can size your energy recovery for that load. Unfortunately, that's really not, as you can see, where a lot of this happens here. So this was a 2,000-ton central plant. They had a heat recovery chiller. Okay, so I don't know how you stop this thing from playing. All right, so you have your heat recovery chiller. You have a centrifugal. You know how to make it stop going? Also?
It's the PowerPoint itself. It's on a slideshow. So for these slides that have that graphics, probably just show them the whole thing.
Okay, all right, well, just go to this one here. And we'll just hit this.
It's going to do the same thing. Though.
Okay, well, I'll just work with it.
Do that.
Yeah, I'll just work through it. It's no problem.
good now.
Yeah. So what they had here is they had a heat recovery chiller. They had a centrifugal chiller for the cooling only loads. You had the building automation system, your cooling tower. They were going to, and this was a new system proposal. They were going to actually propose a fossil fuel gas boiler here. And then once they saw our design, they basically went back and threw in a modular heat pump array to try to capture a little bit more of the energy recovery. As you can imagine, this is going to be very hard to design, install, and commission. By contrast, we, again, no change in performance whatsoever. We were still hitting that 2,000 tons at 150 while also doing chilled water at the same time. And what we're doing here is you can actually get rid of the cooling towers. That saves you a lot of water. At 345 Hudson, just by removing the cooling towers, we'll save 4 million gallons of water every year just by removing the evaporative process. In contrast, now you have these 9 heat pumps. So you have energy recovery in all possible scenarios. So now your graph looks like this. And so every single time there's overlap, you're doing energy recovery. But we didn't want to stop there, right? So we wanted to make the system more efficient. And I think as Chris mentioned, is that you don't need to run the entire system at these higher temperatures if you don't have to. So what we did is we created subarrays. So now you have a cooling optimized array that's hitting your typical chiller conditions. And now you have a higher temperature heat pump array that can do your space heating and your domestic hot water. Because once you're getting to 150, you can decarbonize domestic hot water pretty easily. So now you have an efficient HVAC system that's also doing your domestic hot water decarbonization. But again, we wanted to make the system even more flexible and better. And so what happens if the load changes in the future? This particular customer or building has a data center that might expand or might go away. They don't know what's going to happen. So what do you do to make the system flexible and efficient going forward? And so we kept the same system design, and we kept the cooling array and the heating array, but now we had a swing-over array. And so whatever happens in the future, now these units can hop between the cooling and the heating side. So it gives you the ability to grow that capacity as you need it, dynamically during the day, during the seasons, or whatever happens with the building in the future. So now you have an energy system that's giving you all of the energy recovery with complete decarbonization and adaptive reuse. So future-proof the building as much as possible. And so with the BMS system, you know, that's, again, a lot of the magic happens here with controls. You have BTU meters that are measuring the performance. One thing that I would advise all engineers to do is have real-time calculations on the COP of the system. I've read thousands of specs and have never seen it once, and it's an easy thing to do. And it'll actually tell you how your building is actually performing. So it's one thing to have a COP rating on a piece of equipment. It's an entirely different thing to do it on a system-wide level. And that's really where it matters. It's like, how is your building actually performing? And you can also a little bit see the future, right? And by this, I mean you have a 7-day look-ahead forecast. And where geothermal comes into play here is now that you have, let's say, these hybrid systems where you have geothermal, some air source, and your water source heat pumps, you need to, and let's say you have thermal storage, right? Or phase change materials, you need to know what it is that you can, what is the most efficient systems that you can deploy to meet your load that's upcoming. And with this, now you understand what is coming down in the next 7 days. Let's say there's a polar vortex. You can start charging up your thermal batteries, you can start preheating the ground, things like this that give you the ability to maximize your COP. And so now let's say you have your historical data of each system's performance during a specific given condition. Now you know the conditions that are coming with the 7-day look-ahead forecast. Now you can start really planning and saying, listen, geothermal will just carry me through this whole thing. I don't need to do anything. Maybe I need to do thermal storage, or maybe I need to start using the air source heat pumps. And now you start really having a very effective way of planning ahead. And when you start doing some automated demand response and connectivity to the grid, now you have a grid interactive, efficient building. And so this really gives utilities and the buildings a way to, one, maybe maximize some revenue potential, but also make the grid a lot more flexible. And then this is just a little bit of my experience. If you guys want to contact me, you can use that QR code. So yeah, that's what I got. Thank you.
Thank you. All right, thanks everyone. We're going to open up to questions. Matt is going to walk around with the microphone. Please state your name and organization, please. Thank you.
Yeah, hi, I'm Hugh Henderson at Owagina Consulting. For Chris, so you had talked about cascade systems, and I think you said your overall COP was 3?
Depends. That was an example of 145 degrees of lift with 2 centrifugals in a cascade. So
Gotcha.
that was the worst case scenario in our opinion in that.
And
And very specific. So if we go to different compressors,
Yeah, and I guess I just wanted to, so in a cascade system, you obviously have one capacity, but you pay for power twice. So in kind of simple terms, to have a COP of 3 overall, each heat pump or chiller needs to be running at a COP of 6.
Correct.
So is that what you were saying?
Yep. Yep.
Okay.
There's going to be a higher power draw on that higher temp machine, but overall, yes, it's a
Yeah.
combined COP.
Or I like to say it the other way. There's one capacity,
Yeah.
but there's 2 powers,
Correct.
and so you cut it in half in round numbers.
Yep.
Yeah. Okay. Thank you.
Andrew Macaluso, Watts. This question's for Sean. When you're using transcritical systems, I know a lot of times they're targeted at very high delta T's, high lifts, because it's a requirement for transcritical. How are you able to achieve the low delta T's that are required for a space heating system, and does that have a negative impact on performance?
Great question, and that has been the bane of CO2 systems for most of history, right? So we have a number of new patented technologies that allow for us to do that using off-the-shelf components just in a new way. So in a water-to-water situation, we can go as high as 140-degree return temp, and in air-to-water, we can go as high as 170. Thanks.
I think we had a question up front, Matt.
I guess I have
Microphone.
sort of the same question.
Microphone? Thanks.
The same question. So you're saying that you can have a very good COP even if you're not going up to the 170, if you're just going up to 100, say?
Oh, absolutely. I mean, like you're saying, the lower, we can't break physics no matter what we do, right? So the lower you lower your either supply or return temperature, the more efficient you become. So 5 and 6 COPs are very possible no matter, with a lot of different technologies. Centrifugal's phenomenal with that. But as you start getting a higher lift, your pressure differential goes up. You have to do things like cascades and work in the range. Or if you have a refrigerant with a much wider range, it's not as hard. You can do that as a single lift. And that's what we focus on. And so with that, I mean, let's say I do 95 to 105 standard heating loop for a building. Yeah, I'm going to be sitting in that 4 to 6 COP range, depending on the other source conditions.
Any other questions? All right, if there's nothing else, all of our emails are up here. Additionally, we'll hang out for a little bit afterwards if anyone wants to come up and introduce themselves. And if that's it, I guess we'll let out a few minutes early. Thanks, everyone.